Good morning, everyone. I'm TJ, and today I will run a nonlinear static analysis in NX SOL106, and I will demonstrate snap-through behavior. The benchmark example is from a paper published by P.G Bergan at the NTNU. And first, I will go through some slides, which is part 1 of this presentation. Part 2 will be the actual use of NX. The problems are related to model validation, load control, why it initially will fail and how you can make it work. Then I will go in more details through the displacement control, which is the preferred solution setup in this example. My contact information is here, so you can mail me if you have questions or you want a copy of the models I'm using. The paper is called Solution Techniques for Nonlinear Finite Element Problems. And this means that this was actually an R&D task a few years ago, how to make solvers for this type of problems. While now you have solvers that are accessible in NX, which can step you through these type of challenges. The model is shown in this small image here, and you see it's a spherical shell. The dimension is shown here. And the problem is that initially this shell is linear. It's rather linear at least. Then gradually the stiffness decreases. And here at the limit point you see the stiffness becomes 0, which means that actually no added load can cause a big step in displacement. A snap-through behavior. You can also tell that if you apply like 45 kilonewtons, there is not only one solution, but actually there are 3 solutions, 3 displacements that you can obtain. So you need to guide the solver through these challenges. And if you add load control, you see that you will have these numerical problems. 0 stiffness, negative stiffness, and not only one but several solutions. These numerical problems could have been solved by combining load with arc length control, but that will be demonstrated in another video where I'm using a snapback benchmark. The other approach is to go step by step through added displacements. If you apply a forced displacement, that means displacements control, you will always find one unique solution for any applied displacement. And in this example, the displacement is applied in the center of the shell. The model is quite simple. The average shell element size is 200 millimeters. The thickness is 99.45 millimeters. The material data is simply young the E modulus, 68.95 megapascals, and the Poisson ratio is 0.3. There is no inertia here. It's a static analysis, so there is no density added to the material model. Here we have applied, as I said, an enforced displacement in the center. It's given as a displacement constraint, 300 millimeters in the center. And all other degrees of freedom are free in the center, while all edges are hinged. That means we have 6 X, Y, Z translations and the rotations are free. What I will always recommend when you run a nonlinear analysis is to start with a linear analysis, and you can do that with SOL101. Or you can use SOL106, but then you have to turn the large displacement options off. What happens then is that you assume a linear behavior. So you use the initial tangent stiffness in order to predict the reaction forces. So in this example, if we apply this displacement in the center, the linear solution will get these reaction forces, which are higher than what you will get if you run a nonlinear analysis, where the applied displacement will give you a reaction force given by the interference between this displacement, and the nonlinear curve, the nonlinear path displacement. And then you can see that there is a deviation between those solutions, which is, you can say, is a residual force. However, this linear analysis gives you an initial test on your boundary conditions, the loads, the finite element model, and material data. So it's wise to do an initial linear analysis. Then, after that test, you can run an SOL106 solution. The first thing you have to remember then, which is easy to forget because it's quite hidden in my opinion, the bulk data option here gives you access to the large displacement option. And you turn it on in order to allow for large displacement and nonlinear geometric effects. By the way, we have we are not using a nonlinear material properties in this example. All material data are assumed linear. Then you have to set up the solution, and in the solution static nonlinear main menu, you can apply the case control, and that means output requests and nonlinear parameters. When you have set up those parameters, you can go to the sub-menu, the sub-case menu, and you can activate those nonlinear parameters and output requests. You can also actually model them directly in this sub-menu. In the case control menu, you first have to specify the number of increments. And in this example, we apply 300 millimeters in the center of the shell. And it could be okay to use 300 increments. That means you apply 1 millimeter deformation per increment. The intermediate output flag has to be switched on. That's really important, because if you want to animate or check out the results for each increment, you have to print the results for all those steps. So you either have to choose all or yes. Then I activated iterations before update, or use the parameter 1. That means I want to update the stiffness matrix, the tangent matrix for each increment or each iteration. The convergence criteria, I've used displacement, 1 millimeter deviation from the center deformation. The total is 300, so if you miss by 1 millimeter, it's not catastrophic. The load, I used 1 Newton, which is rather tough requirement, considering the overall maximum reaction force is expected to be like 50 kilonewtons. But these parameters work. Then in the output control, I've specified the single point constraint forces to on, which gives me the reaction forces in the enforced displacement node. And that's all you have to do. Then, if you have remembered to set the intermediate output flag to all, you can animate the displacements for each increment. You have to specify the animation to iterations, not results. Then I'll show you that later. And another important thing is that you have to set the scale in the post view menu to 1. By default, the displacements are scaled to 10% of the model size, which gives you quite crazy displacement for the first iteration. So remember to set the scale to 1. Then you have to plot curves, and unfortunately you have to do this in 2 steps. Hopefully Doug Wenck will get a budget for this at the next release, so we can do it in a more easy way. Right now you have to first plot the displacement versus the iterations, or the load factor, and then you have to plot the forces, the constraint forces in the center node as a function of the iterations or the load factor. Then you have to save those 2 files in AFU formats, and then you have to go to the function tab in the resource bar, and you have to apply or you have to pre-select the two saved functions, and you have to right-click on them and choose two function feature, which allows you to plot then the forces versus the displacements. So you have to do this in 2 steps. And then, if you have done everything right, you will have a curve looking like this, which means that we, by using displacement control, have been able to capture the nonlinear behavior. So that concludes part 2 of my presentations. If you want to try this yourself, you can contact me and I can mail you those small parts and the FEAinME model. It's also easy to recreate them, and NTNU students can simply go to the nxportalen.com and download the models from there. Thanks. Stay tuned. Now I will show you part 2 and the actual use of NX. Welcome to part 2 of this demonstration. Here you see the FEAinME model, which I presented in the first part. And the first thing I'll do now is to create a new simulation. And I accept the default names here. Then I get the solution menu and I choose SOL106 Global Constraints. Then the first thing I do is to go to bulk data and I activate large displacement, LG-DISP. And then I go to case control, and here I first I request outputs, and I use single point constraint forces, and then it's enabled, so that's okay. Then I go to the next parameter, which is nonlinear parameters. I use number of increments. I want to apply a total of 300 millimeters, so I could, for example, choose 300 increments. Then I will apply 1 millimeter per increment, and that's okay. The intermediate output flag, I want to set it to all so I can check the results for each iteration. And iterations before update, I choose 1. I want to update the stiffness matrix for each iteration. And I use 1 millimeter for displacement tolerance. And I can use the same for load. It's quite demanding, but okay in this example. And then I think I'm fine. Nonlinear parameters, output requests, and yeah, that's all I need, and the bulk data. So I press OK, and then I've created my solution. But then I automatically also create a subcase, which I will run, and we want to edit it. And I want to activate the output requests and the nonlinear parameters. And here you see one option is arc length methods, which I will demonstrate in another example. I could have used arc length control in order to apply load instead. That would guide me through the nonlinear behavior and also avoid the problems in the singular positions, the limit points. But now I want to apply a displacement, and then I don't need arc length control. I want to use it. Okay, the next thing I want to do then is to choose constraints, and I want to use user-defined constraints, and I want to choose all the edges along the sphere here, the model, and there we go. And I want to hinge it, so I apply fixed boundaries conditions, no translations in X, Y, Z. But I want to keep the rotations free. That's it. And then I want to apply another constraint, user-defined constraint in the center. Let's make sure that I choose a node, so I choose endpoint there. And then in the Z direction, I use displacement. And then I apply 300 millimeters. And 300 millimeters will be applied in 300 steps. So that means for each step I will apply 1 more millimeter deformations. And that will give me a reaction force in the enforced node, or enforce this direction. So there we are. That's my enforced displacement, and it's hinged along all edges. Then we are ready to run. I have some old results which I delete. but then I choose solution 1 and I press solve. And it performs a solution setup check, and it also display the graphs, the iteration history, and the load convergence. And well, it's ready. So let's check the results. No errors or warnings. Let's check the results. We choose structural and we go to displacements. And as you see here, we have results for each iteration. And we choose set displacement. And the default option when you display displacements is that you scale the deformation 10% of model size. And that's not really a good choice here. We choose absolute and a scale factor of 1. There we are. Then I want to animate the snap through, and we go to the animation task here. We don't want to choose results. We want to animate the results for each iteration, and we have 300 iterations. Sometimes you should use not step size 1, that means show each frame, but we can do it. This example is not very big, so we choose that one. So let's see what happens here. It looks like we have some kind of snap through. It looks like we have added 300 millimeters, and we have some kind of buckling which we want to achieve. So it looks promising, but to just make sure that we have a snap through, we have to plot some curves. And we do it the following way. First, we have selected the set displacement. That's okay. And then we go to create graph. Then we want to select to plot the graph across iterations. And the graph title could be displacement. And we don't want load factor. Well, we could use load factor, of course, which will be between 0 and 1, but we use iteration ID. Step 1, that means for each sample, each increment, we want to check the results. And then we select the center node, which has the enforced displacement, and we press OK. That should give us a new graph. And it looks like this because we apply the same amount of displacement for each iteration, so it's just a linear. The displacement is a linear function of iteration. What we need to do now is to save the graph, and we choose at node 76, which is the center node, and we want to give it a name. So we can choose this one, displacements.afu. Okay. Then we won't need this graph anymore. The next graph will be a plot of reaction force versus iteration. So we choose this one from the results tab, and then we choose create graph once more. Then it pre-selects reaction force nodal, and we don't want to display it as a functional load factor per iteration. And then we select the entity, and that's the center node. We want the reaction force in the center node. And OK. And then let's see what we got. Okay, this looks promising. We see this is iteration, 300 iterations. And that means we have been able to capture the snap through, but we want to plot the displacement and reaction force. That means the equilibrium part. So let's go to the toolbar, and we want to save this graph as well. We could of course have edited the ranges so it captured the whole 0 to 300 millimeters area. Just save this graph first. We could call it forces. Okay, and then OK once more. So now we have two graphs which we have saved. Then we have to go to the resource bar, and we have to go to this tab called XY Function Navigator. And somewhere here I should find my two graphs. We have something called displacements there, and we have the forces there. So now I pre-select displacement and force. And then I right click on these and I select two functions. And I choose the first one versus the next one. That means the displacement will be the x-axis and the forces will be the y-axis. And I create it and plot it. And here you see what I wanted to achieve. This is the snap-through behavior. Here you see the displacement from, it's not 0 but 1 to 300, and here you see the load. And what's interesting here is that we actually applied displacements as increments from up to 300, and at each step we have a unique solution. So by applying the displacement or using displacement control, we were able to capture the snap-through behavior. And we see that the forces looks to be in this right region compared to the results we have in the paper. I could also show you how you manipulate graphs in NX, but that will be another video. But we can state that displacement control is sufficient to capture the nonlinear snap-through behavior. In another video, I will post how you can run a snap-back behavior using force control in combination with arc length control. So stay tuned.